welcome you to the Mid-America Transportation Seminar. As you know, we try and hold these every few weeks. This is the first one since we've sort of all gone on lockdown, so I appreciate you being here. And it's going to be slightly different in that we're going to be completely electronic today. I've asked everyone who's online to mute. It should have come out on mute, but please keep your microphones off. We will be having a moderator, Janet Reno, our MATC coordinator, will be handling that. So if you have questions, please just use the chat and write to her. And when we get to the question period, she'll read the questions out to our speakers, and we'll get the answer that way. So slightly different protocol. As you know, MATC is on, theme of MATC is on resilience to unexpected events, and as such, this is our speakers today fit very well within our topic, our theme of our center. Our first speaker today is Dr. Catherine Stephes, who's a research civil engineer in the survivability engineering branch in the Geotechnical and Structures Laboratory at the U.S. Army Engineering Research and Development Center in Vicksburg, Mississippi. Dr. Stephes completed her Doctor of Philosophy at Vanderbilt as well as her master's, and has a bachelor's degree from Western Kentucky University. Her subject matter expert is in the area of force protection, perimeter security, protective structures, materials characterizations, and weapons effects on structures. And she'll be talking about some of the work in this area today. So Dr. Stephes, welcome, and I'll let you start the presentation. Thank you.
Thank you. All right, let me get this shared. All right, can everyone see my slides, I suppose? Okay, all right. So my name's Katie Stephes. I'm a research civil engineer at the U.S. Army Engineer Research and Development Center. I've been there since 2013, shortly after I graduated from Vanderbilt. I grew up in Southern Indiana, went to Western Kentucky, go Hilltoppers, for undergrad, and then ended up at Vanderbilt. So I've just gradually been moving south. So now I'm currently located in Vicksburg, Mississippi, which is where ERDC is located, the U.S. Army Engineer Research and Development Center. So I'm going to start off by telling you a little bit about ERDC, and then kind of go into one of my first projects when I started at ERDC, which is the Barrier Damage Assessment Module. And then I'm going to introduce my colleague, Bowen Woodson, and he's going to talk about some work that he's doing with vehicle barriers. And then we're going to end up with some opportunities for research, jobs, internships, things like that. So first off, we are a part of the Army Corps of Engineers at ERDC. The Army Corps of Engineers has several mission areas. The one that you probably know about is civil works. So we do things like navigation, flood control, things like that. But in addition to that, the Corps of Engineers also has mission areas in military programs and contingency operations. So we do work with overseas operations, things that are going on around the world with our military. In addition to that, we've got some international and interagency missions. So USACE works with many government agencies all around the world at all times. And then in addition to that, we also do a lot of geospatial work. So the Corps of Engineers was the Army's original map maker, and we continue to have that mission space. Lastly, the Army Corps of Engineers has a research and development mission area, and that's where ERDC, the U.S. Army Engineer Research and Development Center, falls. So ERDC is the Corps of Engineers Research Lab. Across the Army, there's several different research labs, many, and they're all scattered all over the U.S. Most of those research labs fall under the CCDC, the Combat Capabilities Development Command, which used to be called RDECOM. But that falls under now the Army Futures Command, which was recently set up in the last couple of years. In addition to the Army Futures Command, there's a couple independent commands, including the Army Corps of Engineers and ERDC, but also a couple other labs that don't quite fall under CCDC and the Army Futures Command. ERDC gets about 13% of the research dollars from the Army, whereas the Combat Capabilities Development Command gets 71%. So we do some work for the Army, a good portion of work for the Army, but not like the other Army labs. So at the bottom of this chart, you can see 7 different labs, and these are the labs that make up ERDC. This next table or map shows where ERDC is geographically located. So we have 4 labs in Vicksburg, Mississippi. We have the Coastal and Hydraulics Laboratory, the Environmental Laboratory, the Geotechnical and Structures Laboratory, and the Information Technology Laboratory. In addition, we have 1 lab in Champaign, Illinois that's co-located with the University of Illinois. That's the Construction Engineering Research Laboratory. We have a lab in Hanover, New Hampshire, the Cold Regions Research and Engineering Laboratory, and a lab in Alexandria, Virginia, the Geospatial Research Laboratory. We also have field offices located at various locations. One is in Duck, North Carolina, where we have a large pier to do coastal research. In addition, we have a permafrost tunnel in Fairbanks, Alaska. And we also have an office in London, England, where we do a lot of our international work. ERDC is over about 2,000 employees scattered between the different labs, so all over the US, and also one personnel over in London, England. About 60% of those personnel are engineers and scientists. 66% of the engineers and scientists have advanced degrees, either a master's or a PhD. And then about 31% have PhDs. You can see in the age distribution chart that we're a very young workforce, and it's increasingly getting younger and younger. We had a large population of baby boomers, several of which have started to retire already. And then in the Generation X, we didn't have a whole lot of hiring that occurred, so we don't have a whole lot of Generation X employees. So there's a large number of our employees that are younger than 40. So it's a very young workforce. We do a lot of work in partnership. So this spans with our international partners around the world. We have industry partners. We pretty much will work with any company that's doing any type of work in the area that we have interest. We work with almost any university doing research in the area that we do research in. There's just a few on this chart, but there's many other universities that aren't mentioned on this chart. And then we do work with government agencies, almost all of the government agencies. We do work with NSF, we do work with Department of State, we do work with Department of Homeland Security. Pretty much anything that you can imagine, we're doing some work in that area. The work, the type of research that ERDC does across the board kind of falls into what we call our core competencies. These are the things that ERDC is very good at. The first one, blast and weapons effects on structures and geomaterials, that's where the work that I'm going to talk about, the barrier damage assessment module, that's where that falls. And that's kind of my area of expertise. We also do civil and military engineering. This encompasses a lot of different research areas. So things like mobility, bridge loading capabilities, and various other things that could fall under the term civil and military engineering. Also, we have battle space terrain mapping and characterization. That's under that mapping mission that I talked about. And cold regions science and engineering that we do a lot of in our cold regions laboratory up in Hanover, New Hampshire. Military installations and infrastructure, a lot of this work is centered out of our construction engineering research laboratory in Champaign, Illinois, and then computational prototyping of military platforms and coastal river and environmental engineering. The computational prototyping is centered out of our laboratory, our information technology laboratory in Vicksburg, Mississippi, and then the coastal river and environmental engineering is our environmental engineering and our coastal and hydraulics laboratory, both in Vicksburg, Mississippi. So I'm going to start talking about one of my first projects. I did this back starting in 2014, going into 2015 and 16. It's called the Barrier Damage Assessment Module, and the goal was to build a fast-running engineering decision support tool to determine how big of a breach you could have in a perimeter barrier, like at a base camp overseas. So what we found was that Vehicle-Borne Improvised Explosive Devices, VBIEDs, were becoming a common threat to our soldiers that were overseas. And those soldiers lacked the capability to predict if a VBIED was going to affect their perimeter and if the VBIED could get into the perimeter. So if an explosion happened, could another attack, a follow-on attack occur because either our enemies could get through the opening, or they could drive a vehicle through the opening. They could come in with other types of weapons. So we wanted to provide a tool so a soldier could run a very quick calculator and decide if he was worried about a VBIED threat at his base, at his location. We decided to build this tool. Of course, we needed a fast-running engineering model to work so that it could run very quickly. The tool ended up being a computer-based application, and there's a fast-running engineering model that runs behind it. In order to build that fast-running engineering model, we had to gather a lot of information. So we did full-scale experimentation, scaled experimentation, and computational modeling in order to build that fast-running engineering model. For the scaled experimentation, this was done in the U.S. Army Centrifuge, which is located in Vicksburg, Mississippi, at ERDC. The centrifuge, I hope you can see my mouse here. This is the centrifuge over here in the top left corner. And you can see there's a man standing up here. And there's a set of stairs that are normal sized stairs. So this shows you how big this structure is. And the way the centrifuge works is it starts spinning very fast around in circles. And the arm over here to the very far left rotates up so that the gravity acts straight through your model. So as it's spinning, gravity increases, and you get to the gravity that you need in order to scale to the level that you need to scale to. So these experiments that are shown on the screen were done at 1/50th scale and 1/100th scale. The full scale versions are full scale experiments that we ran. At the top, that barrier is about 6 feet tall, and then the bottom barrier is about 13 feet tall. And the 6 foot tall centrifuge model was about under an inch tall. It's 1/50th, 1/50th scale. And then the bottom, the full scale that was 13 feet tall, the centrifuge model was 1/100th scale. So you can see from the pictures that this worked pretty well. We were pretty pleased with the results. The way that we did this was we built the model out of a fabric material, and we used scaled sand. So we used all the fines from a sand material, and we discarded all of the larger particles from the material. And it was able to capture very well. We really concentrated on matching the total mass of the structure. So the model itself was not perfect, but it was very close, and we got the mass right. We also, on the explosive, we really tried to get the impulse of the explosive correct. We didn't worry so much about the pressure from the explosive or the size of the explosive. We worried about the impulse itself. We thought that the impulse and the mass of the structure was going to dominate the response of the structure. And so we thought that was going to impact our engineering model. And we did find that that was true. And these tests helped us determine that this was true. So it helped us define what was important inside of our engineering model. So this is a couple charts. You could tell from the pictures that we did a pretty good job capturing the response of the barrier. But this, I think, really shows how good of a job we did. So these are data points from a LiDAR point cloud that was captured in the full-scale experiment and then also captured in the centrifuge experiment. And you can see on the left, those are both pre-tests. So before the test, you can tell our barriers weren't perfect. Building a barrier at 1/50th scale and 1/100th scale is not the easiest thing to do in the world, but we did a pretty good job considering. You can see the width of the barrier was not quite perfect. It was a little skinnier in the scaled model. But for the most part, we did a pretty good job building it. And then post-test is really where it gets impressive. So at the midpoint of the barrier, this is the damage that you saw in the full-scale experiment in red. The blue is the damage you see in the centrifuge model. And you can see that they align so well that it's it's impressive. And then on the bottom there is the quarter point of the barrier. And again, they align so well that it's very impressive. So for the full-scale experimentation, we did over 10 experiments total, varying different sizes of explosives up to a semi-truck full of explosives and down to about 500 pounds or so of explosives. And there are various different walls. These are all soil-filled walls that we're talking about right now. I'm also going to share in a couple more slides. We did this same type of setup for concrete barriers too. That was kind of phase 2 of this project. But so the barrier in this first video is, it is a 13-foot wall. And that's the one that you saw that we modeled in the centrifuge also. And then the barrier in the other video is a very wide barrier, but it's not quite as tall. It's about 7 feet tall. And it's only one single basket of soil filled. So hopefully these videos will work. It looks like it's very delayed. See if I can get it to work one more time. I can't see the videos doing anything on my side, so I'm not sure that you can see the videos on your side. It's acting like it's working, but it's not doing anything. So the video on the left is a high-speed video, so you can really see the shockwave traveling. In the picture that's over the video, you can see the shockwave as it's expanding. You can also see the explosion kind of wrapping around the barrier. It kind of shows you how blast travels over things and around things. And then the other video was taken from a UAS from overhead, where you can really see the explosion from overhead and how it impacts the barrier. So sorry if you couldn't see the videos. I couldn't see them on my side. I apologize. For the computational modeling, we used LS-DYNA for the most part. We use a lot of different software for our models. LS-DYNA tends to work very well for blast. So in this case, in the end, we ended up using a fully Lagrangian model. But at the beginning, we did some coupled Eulerian Lagrangian models. We used load blast enhance when we used the fully Lagrangian model, but we used factors associated with that based off of what we determined from the Eulerian model. So basically, we do that in order to speed up the model so that we can run them faster. This model can run in a few hours, definitely less than a day on the DoD supercomputer. So we have full access to the DoD supercomputer, and we can run most of our models on there. So these are all run on there within a couple hours. The DoD supercomputer, the High Performance Computing Center, is located in Vicksburg, Mississippi at the Information Technology Lab. So we have very close access to the DoD supercomputer. We can troubleshoot any issues in person, basically, if we need to. So like I mentioned before, we also did the same set of experiments, very similar for concrete barriers. So in phase 2, we started studying the effects on concrete barriers. We got the model, the engineering model, to work very well for the soil-filled barriers, and we thought we could expand it to concrete barriers pretty easily. So we did a few experiments in the centrifuge. We also did a few full-scale experiments. I think we did about 7 total. And then we did some computational modeling for the concrete barriers also. So again, this is the U.S. Army centrifuge located in Vicksburg, Mississippi. There's a man standing up here. So that's how big this structure is. And it is spinning the arm around so that you get gravity to scale. You get a higher gravity on your model so that your whole model scales by scaling laws. So these are 1/100th again on the top, and then 1/50th on the bottom. And the way we did the concrete barriers were we 3D printed them to scale, and then we inserted some copper rods inside of them to get the mass correct again. We weren't trying to model the material damage of the concrete. We didn't expect a whole lot of material damage because we were worried about explosives that were not necessarily touching, or we weren't looking for breaching effects on the concrete. So we expected the whole concrete barrier to kind of overturn and not see a lot of material damage. So since we were not looking at material damage, we were comfortable with just 3D printing with a composite material and not worrying about any type of material damage occurring. Again, this worked really well. It matched up very well with our full-scale experiments. We were very pleased with the centrifuge model, and we feel like we could use the centrifuge if a customer wanted to know exactly what the results were and wanted to see them in person. Without doing a full-scale experiment, we could do them in the centrifuge for very low cost and show any type of customer or anyone who is asking for us to predict something in person. In addition to doing like computational models or something like that, we would have some kind of physical model that they could see and they could see the results. These are some pictures from the full-scale experiments that we did. We did a couple different types of walls. The pictures on the left are a Texas T-wall barrier. I think these are about 6 feet tall. And then the two pictures on the right are Alaska barriers. These are interlocking Alaska barriers. And we did a couple different experiments, one where we cabled the barriers, one where we didn't, to try to see how the cabling affects the failure. But we in total did about 7 experiments and got a lot of good results out of that. This is a video, which I'm not sure if it's going to work, but we'll try it. This is a video of one of the experiments on the interlocking Alaska barriers. Again, these are the ones that are about 14 feet tall, and it doesn't look like I can see the video. I'm not sure if you can see it on your side. Doesn't look like it wants to play. Again, it's a high-speed video, so you can see the explosion really coming over the barriers and even through the cracks on the barriers, which was kind of surprising. Again, I'm sorry that you can't see the video. So again, we used LS-DYNA for the computational modeling. We weren't looking a lot at material damage on these. We were looking a lot at overturning, and the model matched the overturning from the experiments very well. And we're very positive that we can use computational modeling to predict the results of any type of VBIED on a concrete barrier perimeter. We also, in the computational models, could combine the soil fill barriers and the concrete barriers, and we're pretty sure we could get accurate results. We have a few experiments of that, but not enough that we've been able to implement that into the engineering model. So in conclusion, on my part of this presentation, we were able to develop the barrier damage assessment module. So we have an engineering model that works mostly off of rigid body motion. There are some pieces of the model that help us predict the blast pressures that are affecting the rigid body motion. And those are very important to the engineering model that we used. But this computer-based application is available to any soldier. They have to be able to use a DoD ID, their credentials, to access the app. So they put their credentials into their computer, and then it lets them access the app. And they only have to put in a few inputs. What does their barrier look like? What type of soil is it if there's soil? What is the explosive? And it's very general. They don't have to know exactly what type of explosive. They can say it's a van, or it's a truck, or it's a car or a motorbike or something like that. And then it pops out the answer, how big of a hole they're going to have in their perimeter if that type of vehicle-borne improvised explosive device came up to their barrier. And it's very easy. There's some graphical displays. It shows how large the breach in the barrier is. And then also it shares with them some other information that might be valuable, like how large the crater is, so they can tell if a vehicle might be able to drive around the crater and drive through the breach in their perimeter. It also tells them if there will be injuries around that area to humans. So like if they would have lung damage, or if they could have hearing issues after the explosion. So it's a very powerful tool, but it's very simple. It's very easy to use. And it's something that I feel is helping make our soldiers safer overseas. So with that, I'm going to introduce Bowen Woodson. Bowen's a colleague of mine who has been working on vehicle barriers under our Expedient Protection line of research. So I'm going to go ahead and stop sharing and let Bowen take over.
Let me see, make sure that I can get my screen shared here. All right, I hope everyone can see that. So I'm Bowen Woodson. I am a research structural engineer in the Geotechnical and Structures Laboratory. I do a lot of work now under Katie's program for Expedient Protection. I went to school at Tulane University, where I double majored in baseball and chemistry, focusing primarily on baseball, of course, and I minored in math. And then from there, I went to Mississippi State University, where I got a civil engineering degree, an undergraduate degree. And then I went to graduate school in California at UC Davis and got a master's in structural engineering. So I started as a student at ERDC in 2015 and did that as I was going through, sorry, I think I have something on the, okay. And did that as a student, as an undergraduate at Mississippi State, and then as I was still working on my master's at UC Davis, and then came back in full time to work full time. So one of my main areas of research is hostile vehicle mitigation. I'm going to talk today about a barrier that we developed and demonstrated. It's a mouthful, it's called the Field Expedient Non-Lethal Vehicle Arresting Barrier. All right, so we acronym everything in the Army. So we call it the FENVAB, all right? So I'll refer to it as the FENVAB. Okay, let's see. All right. So why is this important, and why are vehicle barriers important in general? And that's because generally terrorists, both homegrown and foreign, are going to attack targets that provide the greatest impact. So that's either going to be a large loss of life, like a big crowd of people, like you see down there in the bottom right, or a critical asset that's going to cause a lot of issues or financial loss. Vehicle attacks have been around for a long time, and mainly when we talk about vehicle attacks, we talk about vehicle-borne improvised explosive devices, or VBIEDs. And one of the most famous ones is 1995, which was the Oklahoma City bombing that killed over 100 people, I think over 150 people, when Timothy McVeigh just parked a truck full of explosives and walked away from it and detonated it. And then, 2017, this is 30 years later, and we're still seeing the same kind of devastating attack. This is in Kabul, Afghanistan, in a diplomatic area that's really crowded during the day. A truck detonated and killed over 100 people. So these attacks have been around for a long time, and they're still happening. They're really hard to mitigate. So that makes it a challenge for us, and it's been a challenge for a long time, and obviously they're still happening. So now we're also seeing another type of vehicle attack, and this is a ramming attack. These have been they've been around for a while, but they've really picked up starting in really 2015, 2016 in the US and in Europe. One of the most famous ones happened in Nice, France, where 86 people died. These attacks are super unsophisticated. They don't take any coordination. It's just one person jumping in a truck and driving into crowds of people. So they're very devastating, and they're very hard to predict, hard to mitigate because of their simplicity. So how do we protect crowds like this, right? Like I said, I went to school in Tulane, down in New Orleans, and there's a Mardi Gras down on the left. When you have crowds like that, in the right, it's a outdoor concert in Los Angeles. We have to worry about people's safety. We have to have a secure perimeter, and we have to have a secure entry control point to limit who gets in and who gets out. We want to restrict vehicles getting in that shouldn't be there, but we want to have an access for emergency vehicles or for police to get in and do what they need to do. So we saw that these types of places can be a target in Las Vegas in the outdoor concert where there was a shooting, right? So where large groups of people gather, we have to find ways to protect those people. So commonly, what we do to protect is set up a vehicle barrier. These are the types of vehicle barriers that you generally see. You see a permanent barrier that's installed into the foundation, which takes time and effort and money to install. And it allows, like I said, it can restrict certain vehicles, but it's an active barrier, so it can move up and down, and you can allow cleared vehicles to access the site. On the right is just a little temporary barrier. This was at one of our colleagues took this picture last year at the World Series, and it's just something they throw out there real quick. Obviously, you can't move them as easily to allow vehicles to have access, but they're also important in securing your perimeter. So what we developed, and really starting about 10 years ago, was the FENVAB. Development began where what we were wanting was something that was used very simple materials. We didn't have a whole lot of engineering support, didn't require a lot of tools or specialized equipment. And this was something that we could just give drawings to a forward operating base or someone overseas, and they could quickly assemble this as they're moving across a war zone. And it's an active barrier. It can be deployed in under an hour. So you can have vehicles, you can allow access to your vehicles and restrict it to enemy vehicles. And the way that it works is it is based on a friction design. So you see the chain link fence there. It acts as a mat. And when a vehicle impacts the uprights of the barrier, the tires stay on the mat itself. So the vehicle will enter a skid because the tires are no longer in contact with the road. So as the tires try to spin, they can't gain traction. So eventually friction will cause the vehicle to slide to a stop. So as I said, we've been working on vehicle barriers, expedient vehicle barriers for the past 10 years. And this is kind of our spiral of development. We've tried lots of different things. In 2013 was the first time that we started testing the FENVAB. And at that point, we had two prototypes for the FENVAB. We had the lambda barrier and the L barrier. They effectively did the same thing, relied on the same materials, but they were just two slightly different styles. They were modular, but we had not actually tested them with multiple units linked together. We'd only tested them against smaller vehicles, just a single unit against smaller vehicles. And last year, we did our first test where we linked several of them together. The lambda barrier, we did some modifications, and we tested it against a larger vehicle. So currently, we're still working, right now under Katie's program, my team is working to develop another barrier that's expedient, that's similar to the FENVAB, actually uses the same active barrier, the same technology, but it's packaged a little bit different and it's a lot cleaner and more kitted, whereas the FENVAB was something where the purpose of the FENVAB was to make it very simple. So really anyone with a set of drawings can just go into their local vendors or suppliers and pull the materials and put this thing together. So we do have patents on our barriers. So we've developed, right now we have 3 patents. So the FENVAB is one of barriers we've developed. We also have another one that has been under development for the past 4 or 5 years, and it's kind of coming to its finish line. And we're seeking a patent right now for the DETER, which is Deployable Expedient Traffic Entry Regulator. That's the one, another acronym. That's the one that we're working on currently. So as I talked about, we had 2 different prototypes. This is on the left, that's the L barrier, and the pieces are shown on the right. Basically, you have horizontal base section and then a vertical section. It all connects to a chain link that's used as a mat. And this is the same concept, but this is the lambda version. This has a horizontal base section, and then you have the diagonal arms. And then there's these straps you can see, support arm beams. They link that those diagonal arms to the horizontal channel. And that's where a lot of the load is transferred at impact. So this is assembly. This is us putting it together last year for the demonstration. The only tools that we have there are those little crowbars that we're kind of wiggling into place. We use a forklift to drop all of the materials in place, and we just use a wrench and a pry bar, and that was it. And then that's on the right, that's us. I'm the one really struggling right there. I'm pulling some cables and just weaving them through by hand, just weaving them through the chain link, and that attaches, the cables themselves attach to the base of the barrier. And it kind of acts like a frame, the cables do. That's where all of the load is transferred through. And then the mat, or the chain link, kind of acts like a mat, or it's kind of like a decking where the tires sit on it, but most of the load is actually being transferred through the cables. The left shows the finished version. The right shows the fence hooked into the front of the base of the barrier, and we have just an angle and a flat bar bolted in. It kind of sandwiches that fence in there, so that keeps it secure. You know, concern is separating the mat from the base of the barrier, so we have to be very deliberate about how we make that connection. Another really cool thing about the FENVAB is when it lays down, you don't have to lay the whole thing down to allow access to vehicles. So this shows if we just lay the middle sections down, we can allow access to a large truck. We could also leave the middle section up and lay the outside sections down, and that would allow 2 lanes of traffic for small cars. So how do we do this? How do we do our research and development at ERDC for all of these vehicle barriers that we've worked on over the past decade? It includes really, I guess, 3 phases. There's LS-DYNA modeling and simulations, which is very important. We do an experiment using the remotely piloted vehicle system that we have, RPVS, and that was developed by ERDC. And what it is it's a way that we can safely guide the vehicle down into the barrier without a driver, so we don't actually have to put anybody in there with shoulder pads and a helmet. We just hook this system up, and there's a guy that sits off to the side, and it's like he's playing Mario Kart. He sits there and drives this thing flawlessly down a lane and impacts it at whatever speed we tell him to. It's very impressive. And we also, put accelerometers and strain gauges on our barrier and on our vehicle, and we can, 1, validate the model, and 2, we can see how much damage we're incurring on our barrier. And also another thing we can do is we can track the acceleration, velocity, and displacement of the truck. So how far it slides, how quick that drop in velocity occurs. And then we just go back, we refine our model, and then we may do another test. And it's just a circle as we continue to push out new types of barriers or push our barriers to new limits. Maybe I will have more luck playing videos than Katie. Let's see. So this is, I can see it. Hopefully y'all can see it. It is a truck, LS-DYNA simulation of a truck impacting the FENVAB. And this simulation was not done by me. It was done by another guy in the survivability engineering branch, one of our colleagues. And this truck was not developed by ERDC, the truck model. It was actually developed by Federal Highway for their crash testing. It's very important to get a truck that behaves and deforms like an actual truck. You can't just use a solid block of mass and run it into it because it won't behave the same. There's a lot of assumptions in any model that you make. One of the primary assumptions here was coefficient of friction. It's a friction-based design, so we had to assume a coefficient of friction, which may or may not, be what we actually see on test days. But so we take our best guess and try to get a prediction based on the model. So we also in the actual experiment, we put some strain gauges on those straps that I talked about that connect the diagonal member to the base section. So we wanted to see what kind of strains we were getting in our model. So prior to the test, we took at 8 locations. I don't show 1 and 8 here. 1 and 8 had really high strains, and the reason those strains were particularly higher was they are on the outside, and the span from that strap to the next strap is much longer, whereas the other ones are caught in between the middle, so they have lower strains. So I only show 2 through 7 there, but they're all about the same. And then this is the crash experiment. Hopefully you can see this. This is the fun part. has a little noise. I don't know if you'll hear it or not. There might be a lag too. I think it might be lagging. But this is the vehicle. This is being remotely driven by our team. Like I said, they're pretty impressive through the cones. And then it just impacts and skids to a stop. There's a few different views, hopefully you can see. Hopefully you're seeing this. There's also high speed here. And then you can see how it behaves, kind of the wave of the mat, also how the truck comes off the ground slightly in the experiment at impact. And then you see in the model, it's really the same type of behavior. The model was actually a little more conservative. There was some shearing of some elements early on. Actually, there was some shearing of those of the connection of the straps to the base, and that's why we put the strain gauges on those straps. That's why we chose that location, was because we thought that was going to be a critical location. So we got the strains from the model so we could compare them to the experimental strains. And we also did a few modifications prior to the experiment to beef up that section. We added some thickness to the straps around the bolt where it was shearing. So that's one benefit of LS-DYNA. It's a very cheap, or a much cheaper way to inform us on our barrier design, other than doing crash tests over and over again, which are not so cheap. This is what it looked like following the crash. So you see there's lots of damage there on the truck. We call this the FENVAB, and the N in FENVAB is non-lethal. And you can see in the cab there, it's really not damaged at all. If I had a picture inside the door, which I don't, you could see that there was no damage to the inside of the cab. So the driver likely wouldn't have sustained wouldn't have died, and probably wouldn't sustain serious injuries. The airbags did not deploy, but the truck was inoperable after. It could not be separated from, we couldn't put the truck in reverse and back it out, right, and then do another attack. We actually had to get, and you can see picture on the left, a forklift and pull the rear of the truck, and on the right we had to pull with a winch that was hooked to a F-250 and separate the barrier from the truck that way. This is a picture of the barrier following the crash and the truck. So you can see there's significant damage to both. So I talked about instrumentation, and the accelerometers was one form of instrumentation that we did in this experiment. We had two accelerometers, one at the front of the truck and one at the back of the truck. And let's see. So this is the general shape, or what the acceleration, velocity, and displacement looks like. So on the left, the red is the acceleration, whereas the blue is the velocity. It's really cool, I think, to look at the velocity on the left. You can see as it's climbing, or as velocity is increasing, it stair steps, right? Let me see if I can use a mouse here. There's spots where it plateaus, right here and here, and that's points where we actually shift gears, right? So we're not getting any acceleration. So that's really cool to see those little intricacies in your data. And then this point where acceleration jumps up and it peaks, that's impact. So the velocity drops really quickly to this point, and then it begins to skid until it comes to a stop. And then on the right, we have the same thing, right? The blue is the velocity and the red is displacement. And you can see the same trend. And we took we started integrating at this point where we thought it started to skid. So we didn't integrate here to get our distance. We integrated at this point. And that's how we were able to check to see that we're getting the same distance that we physically measured from our accelerometers. So it's just a good sanity check for us. And they did match pretty well. So we also had, like I've said, the strain gauges. We had 6 strain gauges hooked up to different straps. And you can kind of see the picture on the right, I think, shows best the direction of the strains. These are little gauges right here. And then this is an overlay on the left of the LS-DYNA and the the experimental strains. So on the left, so the time is off because it's an arbitrary time. LS-DYNA they were not, it wasn't at the same time. We didn't have to drive it down in LS-DYNA for 400 feet before we impacted it. So the times are different, but you can see the magnitudes are very similar, especially for strain gauge 5 and the LS-DYNA strains. The only one that had significant plastic deformation was the strain gauge 4. And you can see by looking here at the barrier itself, not all of the arms, right, are up forward direction with a lot of plastic deformation, but these in the center were most impacted, and specifically the arm that had strain gauge 4. So that was good to see that our strain gauges were giving us the same data that we could see with our eyes. And as I talked about, we're currently working on developing another barrier, and this is just conceptual drawings where we're integrating that same, you can see in the top right, that same type of barrier, that same active wedge barrier into a quad-con. Quad-con is 8 feet wide by 8 feet high, and this can be delivered to the site by a forklift or a specialized vehicle, PLS truck, that will just drop it into place. And after it's delivered, you can just maneuver it where you need it. It's modular. You can put as many of these side by side as you need. And then the walls and the roof just unfold. It has a mat. It's made of a different material, an ERDC developed material called ACE mat that's used for vehicles trying to cross in soft terrains. So this is a very durable and flexible material. So you can just fold the mat out like an accordion and it's in place. It takes less than 30 minutes is what we're hoping we'll accomplish with this one. And it's the same type of technology. It's just a different approach, right? This is just a more kitted solution, nicer looking, but it's more specialized. Like it's a commercial off the shelf technology. All right, so that's really it for the FENVAB and for vehicle barriers. And I'll probably pull Katie in on this. She knows this probably better than I do, but we have job opportunities and opportunities for students, many different opportunities for students. One is called the Pathways program, and this is the program that I was on as a student, where I came in on the summers and Christmas break or spring break, or really whenever I wasn't in school, and I could work. And it was great for me. I learned a whole lot in those years where I was a Pathways student, and the job was always there, right? So I didn't have to worry like some of other guys that I was going to school with would worry about where they're going to work that summer, what their internship's going to be. I always had a spot, at ERDC. And once I graduated, I just converted over to full-time, and it's very easy for them to convert me over to full-time. So it's a great program. We also have the College Qualified Leader, CQL. That's kind of like a mentorship type program for undergraduate students where you're actually matched with a mentor, and they kind of guide you through. So it's also a great program. And we have the SMART Scholarship, which is awesome. Katie was on that one, so she can probably talk more about that, but it's a pretty unbelievable program, in my opinion. But Katie, do you want to talk more about SMART?
Yeah, sure. So the SMART Scholarship Program is what I got when I was doing my PhD at Vanderbilt. And it's a program that they link you up with a sponsoring facility. Mine was ERDC. And your tuition is paid for, your books are paid for, your insurance is paid for, you get a stipend, which is very competitive. It's actually higher than the NSF stipend. And it's a very great program. At the end of it, you are required to work at your sponsoring facility for the amount of time that you are on the scholarship, which is a great thing because you have a guaranteed job. Also in the summers, you do internships. And in most cases, especially for PhD students, usually your research aligns with what you're doing for your PhD. So you get some extra benefits on working on your PhD. You have extra resources like laboratory space and things like that. So it's a great program. I highly recommend it to anyone who asks. I guess I can continue. There's a corner down here with job opportunities. We publish our jobs to the usajobs.gov, but we also have direct hire authority. So we sometimes publish direct hire opportunities on our webpage. And you can also directly submit your resume to the web address that's down there, erdicrecruiting@usace.army.mil, and we'll get your resume directly. Lastly, the bottom thing there is the research opportunities. Those are broad agency announcements and other announcements that are made from ERDC and from other government agencies. So if you're doing a postdoc or you're a professor, there are things that are announced on there where there are research opportunities available.
Yep. All right, and that's it. If we have any questions regarding either of our presentations for the technical stuff or for job opportunities or for what ERDC does and what ERDC is, we'd love to answer those now.
Well, thank you very much. That was a great set of presentations, and we'll open it up for questions now.
I do have one question from Ron Faller to Katie. What maximum pounds of equivalent TNT were used in testing? Also, what lab location was used for blast testing?
So on the barrier work that I presented, we had the opportunity to do a lot of collaboration. So we actually tested up to 30 metric tons, 66,000 pounds of TNT equivalency for some of those tests. But we also tested down to a couple thousand pounds on some of those tests too. So there was a wide variation of explosive TNT equivalency that we used. Those tests were done in various locations. ERDC does a lot of their blast testing at our facility it's called the ERDC Test Facility. It's at Fort Polk, Louisiana. We also have some range space at Eglin Air Force Base. In those ranges, we can do up to 10,000 pounds at Fort Polk. We can do up to 20,000 pounds TNT equivalency at Eglin Air Force Base. We also do testing all over the U.S. We use Dugway Proving Grounds. We've done a little bit at Aberdeen. We do stuff at Fort Bliss, China Lake, many different places. We've also done testing, large-scale explosive testing overseas too. So we recently did a test in Sweden. We've done tests in Canada and Australia. We do testing in Israel, Germany, UK, all of our foreign partners, basically we do testing with them too. So many different locations and many different charge sizes. And we've done much larger than 30 metric tons in previous different experiments.
Thank you, Katie. Another question for Katie. I assume the perimeter protection barriers you have shown are chained or continued. What if a barrier already has a slit or an access point? Would the result of the breach change dramatically in BDAM module? So
BDAM does not have the capability built into it to do an opening in the barrier. But we did kind of in the experimentation look at like edge effects, what happens if breach were to occur near an edge. And yes, it does have effects because you have less mass there. So yes, I do assume that there will be dramatic changes. It's not included into the barrier damage assessment module, but it is something that we can do with our high fidelity computational modeling.
Thank you, Katie. I have another question from Ernest at UNL. Is the model able to predict the effect for a combination of explosive?
What does he mean by the combination of explosive?
All right, Kati, you had 3 different types of explosive that you indicated that the soldiers can use in the software to determine how they are able to find out the effect on their facility. So I was asking, is the model will be able to determine a combination of those explosives, or it's just one explosive at a time?
It is one explosive at a time, as it is in the module right now. But if you could predict blast loading from combinations of explosives, which we have the capability to do that, then you could theoretically do that determination. It's just not included in the app that we share with the soldiers. And actually in the app, we don't really, there is an advanced portion of the app where you can go into the advanced module and you can change the explosive type. But for the soldiers, we don't, we have a version that you don't even choose what explosive type. We just make assumptions based off of the size of vehicle they're looking at. So it's very simplified down.
Hi, Katie, I had a couple of questions for you. Specifically, you're looking at your LS-DYNA model. When you were looking at your Lagrangian model, you noted that that was done for speed with the soil material. You mentioned you also had done some work with the MMALE. I was curious if you had tried any DES or SPH type of modeling approaches for your soil.
So I did not do the modeling. Don Nelson, he's very well known in the LS-DYNA world. He did all of the LS-DYNA modeling on this. I do not believe that he tried anything else. He has many years of experience, so he kind of went into this problem knowing what exactly he wanted to do already. But we've also been working on the modeling with our international partners with both Germany, the Ernst Mach Institute, and with DSTL in the UK, and they have tried many other different types of models, including outside of LS-DYNA. And we have compared the results with Don Nelson's LS-DYNA model, and his model currently seems to be working very well. Several of the other models also work very well, but Don's model is working pretty well for all the experimental results that we have. Sorry, I can't answer that in more directly, but I do not believe he did try anything else.
All right, I do appreciate that. And if you were looking at soils for different types throughout the world, let's say you're applying your different soil materials, do you expect there to be a significant difference in the performance of these soil filled barriers if it's in cold weather conditions that could contain ice, if there's heavy sand, if it's clay, etc.? Do you expect to see large differences in performance, or is it basically a mass inertial barrier?
For the most part, it's mass. We did some parametric studies. There are some differences depending on the soil type, the density for the most part, but they're not substantial enough to cause significant differences in the results. So it's kind of one of the variables that if you do have the capability to pay more attention to it, you should. But if you don't have any way to estimate what type of soil properties that you have, then it's fine to assume something in the middle.
All right, thank you very much. And I also had a question for Bowen, if we're moving to that too.
While we're on the topic, Katie, Dan Lenzel is interested if discrete particle models were used for soil and were temperature effects considered in the DYNA models?
I do not believe we did temperature effects at all. And I cannot remember any of our international partners doing temperature effects either. For the discrete particle models, ERDC did not produce any discrete particle models. Not for this problem specifically, although we do it for many other problems. But I do believe that some of our foreign partners did use some discrete particle models for this problem.
Thank you. Let me look at the questions here.
I apologize. Katie, I have one more question. This is Cody Stoley again. With respect to your blast wave, both testing, modeling, and applications, did you see a significant effect that the blast itself had on barrier performance versus just simply a RAM-based application?
So we never really looked at that specifically. And we have done some like vehicle ramming into these soil type barriers. But we were never really investigating the two side by side or anything like that. But we did do a couple different explosive loading scenarios. We did one where the explosive loading was pretty close to the barrier, so you kind of get more of a breaching effect. And we did a second one. We've done several tests where the explosive loading is a little bit further away, and you get more of an overturning effect. So there's definitely differences in the way the barrier behaves based on the loading. And it's very clear in some of our experimental results how different those behaviors are. And it's important that we capture different methods of failure too, because it does affect the breach width in the results of your predictive model too. So
we have a follow-up question on soil from Ron Faller. He'd like to add or ask if moisture effects were considered in soil perimeter barriers.
Yes, ERDC did not look too much into moisture effects, although we did capture the moisture content of the soil when we were doing our experiments so that we could compare them. But both the UK and Germany together have looked extensively at the moisture effects in the soil barriers. One thing that they found in partnership was that the moisture tends to kind of pool at the bottom of the soil barriers. So you've got right at the base of the soil barrier, you've got a large amount of moisture down there. And it significantly affects the barrier because it will easily overturn with all that moisture at the bottom. So there's been some extensive studies, and they've done some reports and some papers on that topic. And I believe they've done a couple conference presentations on that topic too.
Okay, I've got several questions for Bowen. Is the barrier anchored to the ground?
No, so all of our expedient barriers that we've developed, it's kind of our little area of expertise, I guess. None of them have anchors. They're all friction-based. So because we're trying to deploy these very quickly, we don't put any anchors in, which is helpful for getting them deployed quickly, but also, you know, what it does allow, it's going to allow greater penetration. So we expect to see greater penetration of our barriers than, you know, these classical wedge barriers that are anchored directly to the ground with a, you know, big foundation. But no, we don't have any anchors in any of ours.
Okay, follow-up question, is the barrier considered as active or passive protection to the aggressor truck?
It's active because we can move it up and down. So the FENVAB, as it stands, the version that you saw there, someone has to actually go up to the FENVAB itself and get on the barrier, and they push up on it and they can pull a sleeve and it drops into place. The barriers that we're developing now, the kitted solution, is going to have some type of hydraulic or mechanical component that will allow the operator to stand off to the side and do that much easier.
Okay. Would you remind the group what the test speed and the weight of the truck?
So the truck is the largest truck that you can get without a CDL. And that's why we picked that truck, so you don't have to have a specialized license, so that anyone can, you know, just jump in it. And unfortunately, I can't speak to the impact velocity for that specific test. I wish that I could, but I can't. That's one of the details that I can't discuss.
Okay. And final question for Bowen, was the performance of the barrier analyzed based on the angle of impact?
So we assume 90-degree impact. Because that's worst case scenario, right? Is hitting it head on. And I know in so the standards, ASCE assumes that there's 90-degree impact, but in the international standard, the IWA, there's you manually, or you can put in the penetration rating the angle of impact. So they test that really a wider array of angles than we do generally in the U.S., I guess, with because we follow ASCE F2656. We did not rate our barrier to either standard, but when we do our crash experiments, we always do them at 90 degrees.
Great. So that was the end of the chat questions for Bowen. Cody Stoley has a few questions for you, Bowen.
All right.
Hey,
You actually already answered at least one of those. But with respect to your remotely piloted vehicle system, do you have a maximum speed that you're able to achieve with that system?
I'm not sure if there's a max or not, but we have, in ASTE, in ASTM, you can hit an impact speed of 60 miles per hour, I think is the peak. And we can hit that speed with the remotely piloted vehicle system. They've recently upgraded that system, so there is a little bit of a lag when they give a command. So when they steer, there's a little bit of a lag. It used to be much larger. Now it's almost instantaneous. So it's really easy, even at high speeds, like 60 miles per hour, for them to drive it down there flawlessly. Probably better than I drive on a regular basis.
But you are suggesting that this system is essentially just an override of your typical ICE. Is that true? I mean, internal combustion engine, you're applying pressure to a gas pedal and steering it through some kind of a steering mechanism?
Yeah, so what it is in there, there's like little kind of pegs in there that as he presses the gas, outside of the vehicle, it pushes down on the accelerator. So it's mechanical. It actually pushes the accelerator. And there's another mechanical setup that actually steers the car. As he gives the command, there's something in there actually steering it.
Do you have any concerns, considerations, questions, or have you ever had any complications with ruptures in fuel line or battery problems? With a lot of our MASH crash testing, we have to use hermetically sealed batteries and remove fuel from the fuel compartments just in the event of a rupture.
Yeah, so we do all that. We get as minimum, amount of fuel that we can get in there. We have another branch within GSL called the Mobility Systems Branch, and they've developed this technology. So we usually bring them in to conduct these experiments for us, and they have a full, checklist. There's also some safety features, like if they lose contact with the vehicle, it'll shut down immediately. But yeah, we do the same thing. We remove almost all of the fuel. There's just, if it gets off course by a certain amount, it'll shut down. So it's a pretty cool system, pretty advanced system. We have, I've heard people, I mentioned people getting in, shoulder pads and a helmet and driving down there. I've heard of people actually doing those at lower speed impact tests. This system is, I'm glad that we're not using that. This system's been awesome for us.
Yeah, we do have an application of using that similar kind of a system where we use a hydraulic presses. Is your system reusable, or do you ever experience any damage under a high G frontal loading? In the experiments that I've conducted, we didn't significantly damage it. I don't know that if they've ever had heavy damage on there. I mean, I'm sure, depending on the impact, right? All of our barriers thus far have been non-lethal barriers. So we don't see, stopping it, point blank. So there's not as much damage to the vehicle itself. But I imagine if we did a test like that, there would be damage to the system. But fortunately, I haven't seen that yet. I appreciate you keeping up with all my questions. I had one last one. Do you use any high friction treatment on either the asphalt or the concrete wearing surface?
No, we haven't.
Barrier system.
We hadn't before. We just put it on, like on that one, we just put it, it's a regular chain link fence, and we just put it down on the asphalt. And the day that we did that test, it was actually raining a little bit, so that hurt our friction some. So there's variation, right? It can go on a lot of different surfaces, but there's going to be a lot of variation in penetration based on if it's wet, if it's dry, right? If it's a brand new asphalt, if it's worn down. But now we haven't put any treatment on there. And the people who were involved in this program before me did a lot of studies on friction and how it affects performance. And what they saw was that friction is really hard to, it's really hard to increase your friction in an experiment like this. You can do, using different materials and things, but in the end, the penetration is, I think, mostly controlled by, the amount of energy that you're impacting, the mass of the vehicle, the velocity of the vehicle, the mass of the barrier. So it's hard to really change coefficient of friction, I think, from what they've seen in their studies.
Thank you, Bowen. Just one comment for you and Katie from Dr. Linzell. You may already be aware there was a study completed by the Department of State Overseas Building Operations focused on shallow foundation, easy to install barrier systems to protect interests.
Yes, thank you. That was included in some of the data that went into the barrier damage assessment module. One of our colleagues was heavily involved in that testing.
Great.
So I think that's it for the questions. Am I correct, Janet?
Yes, that's it on the chat.
Okay, so Dr. Stevens, Mr. Mr. Woodson, thank you very much for participating in our seminar series. I think everyone's aware that the original intent was to have you here, and we look forward to having you visit us on the other side of this COVID-19 crisis. But it was a very interesting presentation. You can tell from the questions we have a lot of interest, and I'm sure just for the people on the call, if you do have other questions, I'm sure Dr. Stevens and Mr. Woodson would be happy to answer any questions after this as well. And our hope is to find some areas of cooperation, so we look forward to working with you in the future. So thank you very much. Have a great weekend. And with that, I'm going to end the seminar. Thank you.
Thank you.
Thank you.